Let us see the addition of alcohol. See, even this addition is of Markovnikov type, just like the addition of water. Here we get OME. In this case also, addition is according to Markovnikov. And of course, rearrangement is also possible. So Markovnikov addition, just like the addition of water, I mean, acid catalyzed hydration, this is the addition of alcohol in the presence of acid catalyst. It involves rearrangement also. Okay. Now, just like oxymercuration, demercuration, there is something called alkoxymercuration, demercuration. Even this also is a preparation method of ether, just like the previous one. In this case, look at this. Now, in the first step, let us consider mercuric acetate. Normally, we take water, but here we consider an alcohol. So, that is the difference. Okay. This, in fact, goes via Markovnikov plus a no rearrangement. We know that. Now, according to Markovnikov addition, it will be like, I mean, the OR from this. Okay, here you get OR, and here, of course, HgOAC. We have seen the mechanism of OMDM, oxymercuration, demercuration. Alkoxy group from the alcohol comes into picture. RO minus and H plus. So RO minus is added according to Markovnikov to this particular carbon. Now in the second step, I mean demercuration, take sodium borohydride as usual, from which we'll be getting a hydrogen. Okay, here it will be the hydrogen what we get. No problem. This can be written as OR here, and this is simple CH3. So this is alkoxymercuration, demercuration. In fact, the formation of an ether. Even this also is an ether. Here also. Preparation of ether. Okay. Next. Now, there is a reaction called Woodward's reaction. Again meant for syn hydroxylation, but the reagent is different. Let us consider this particular compound, a cis-1 cis-butadiene, and here the reagent used is silver carboxylate along with iodine, followed by hydrolysis in the presence of base. In this case, we get syndiols like this. So a syndiol is what we get in Woodward's reaction. Okay. Next. Let us take some other reactions. Like the addition of alkane. See, in the addition of alkane, you can again cut it like R minus and H plus. Consider alkene, the same propene, this, to which RH is added. Okay. This can be carried out in the presence of an acid or at a high temperature of 500 to 600 degrees centigrade. In fact, this goes via a free radical mechanism if you consider higher temperature. It's very simple. It's either you can take R, see in the presence of H plus, it will be like R plus and H minus. The addition of R plus and H minus according to Markovnikov. You can go this way, or else even follow a free radical mechanism. Okay, so here we get R because this is where we have added H minus. No, R plus and H minus. If suppose this is considered, we have added H plus. Then R, no, H minus and R plus. H minus is added here, R plus is added here, right? That is according to Markovnikov. Let us see the free radical mechanism of this. It's simple. Markovnikov addition of H minus, the negative part gets added here and the positive one gets added here. Let me give you the mechanism, the free radical mechanism, or the ionic one. Look at this mechanism. The first step is addition of H plus. Markovnikov. Of course, the same, no big issue. Get the negative thing here, positive thing here. That's it. Simple addition. Uh, we get a positive charge here. Of course, H plus is being added. Then take alkane now. I've added H plus already. So then go with this R minus. So you'll again get a H plus. I'm sorry, first step is the addition of, just a second. After, just a minute. Now, initially, we add H minus, right? H minus and R plus is what we have to add. H minus when added will give us, yes, simple alkane and R in the form of R plus. Yeah, because it is the addition of R plus and H minus in the presence of acid. Yes, I've added H minus. That is how we got R plus. Now, see in the second step, anyway, we got R plus. Now that R plus will attack on the alkene again. It can be shown this way, or let me show you the other way. Here we get negative charge as usual and a positive charge, of course, then negative to positive. Same. Now we are adding R plus. In the first step, we have added H minus. Come on. This one, uh, of course, there will be a positive charge. Then the thing that is added, R. Now the positive charge requires a H minus again. So let us consider another alkane. Yeah, this minus will now attack. So the thing that we get here is, yes, R. Anyway, H minus is added here. And we again get R plus. This is how the reaction just goes on. So it's simple Markovnikov addition of H minus. Now it's R plus. H minus and R plus. That's it. Okay. Now let us see some other named reactions. Now there is something called oxo process, or is also known as hydroformylation. Okay. See, in this reaction, we'll be adding CO plus H2. Now a mixture of these two is actually called water gas, right? This is done in the presence of dicobalt octacarbonyl. So this is a coordination compound. Dicobalt octacarbonyl. Look at the way I've written them. This is cobalt and this is carbon monoxide. Okay. Now it's simple addition of H minus. See, this of course can be written as H minus and HCO plus addition according to Markovnikov. Markovnikov addition of these two. Come on. We get CH3, CH, yeah, anyway, it will be like this, right? CH2 minus and then H plus. Add H minus. Okay. Then this one. CH3, CH2, then CH2 to which the CHO is added. It's nothing but an aldehyde. So this is how we get a carbonyl compound. Okay. Of course, this is a major product. Then let us take another named reaction called Walker's process. Even this also is a preparation method of aldehyde, as in the previous case. See, when ethylene gas is passed through a solution having an aqueous solution having palladium chloride and cupric chloride. I need to actually consider water molecule rather than writing this aqueous. Let me take water here first in the presence of cupric chloride. Yes. Aqueous palladium chloride is this. Now we get an aldehyde. Look at this. Simple, just a second. CH3, C double bond O, H. A simple reaction, you can eliminate HCl, just add this oxygen to ethylene, right? Of course, after rearrangement, you get an aldehyde. Aldehyde, then of course, palladium along with that HCl. So this is called Walker's process, a preparation method of aldehyde. Okay. Next. Now, another named reaction. So this is Koch reaction. See, when propene is treated with carbon monoxide and HCl, in the presence of anhydrous aluminium chloride, followed by hydrolysis. Now, in this case, we get a carboxylic acid. This is a little interesting. Let me actually give you the mechanism. Now, let's see how the reagent is added to propene. Starting with propene, let us add HCl in the presence of anhydrous aluminium chloride. See, as I told, the Lewis acids are generally meant for getting an electrophile. Come on, across the multiple bond, if suppose H plus is added, of course, Cl minus goes along with the AlCl3, which is a Lewis acid, right? That means it goes out as AlCl4 minus. Come on, CH3, then CH. Here we get a positive charge because anyway this gets negative charge and this gets positive charge. So the negative abstracts H plus. You know the mechanism. Then this will become CH3 because it's CH2 minus and H plus. Right? Now to this carbocation will be adding carbon monoxide. See, carbon monoxide along with the formal charges can be represented this way. This is very interesting. See, carbon has 5 electrons around it, 2 here, 3, 4, and then 5. That is the reason why it has got a negative charge. Oxygen also has 5 electrons, but one short of what it has to have. Being a sixth group element, it has to have 6 electrons, but it has only 5. So, got a positive charge, right? One second. Oh, okay. Yeah. Now, this is what we are going to add. Yes. Come on. See, then this gets connected here. Normal. Then what do we get? CH3, CH. Of course, the C triple bond O. But this oxygen has still got the positive charge, right? Now, this is when we add the second thing, that is water molecule. Okay, now when water molecule is added, look at what happens. Water molecule can be taken this way. Now this will get added to the carbon. At the same time, a pi bond goes to the rescue of the positive charge. Okay, then what do we get? CH3, then CH to this carbon. Of course, this has become C double bond O, and of course O H H, a pair and a positive charge, right? Then of course the CH3. Is this okay? Now, final, of course. Final thing is, yeah, look at this one. Minus H plus. See, in the first step, we have considered H plus, and now we are losing it. So finally we get CH3, CH, C double bond O, then OH, of course, carboxylic group, then this CH2. So the mechanism is quite a lot interesting. Okay, check this out. Next, let us take some free radical reactions. Okay, see in this case, say when a propene is treated with, let us consider ICF3 in the presence of sunlight or UV light or in the presence of a peroxide. Yeah, these are in fact meant for getting the free radicals, right? So what do we get? We get CH3, CH. Of course, these all go as per anti-Markovnikov addition. CH3, then CH. Yes, we get iodine here, then CH2. To this CH2, of course, CF3 gets added. You can actually remember it this way. The negative part goes to that carbon having more number of hydrogens. Of course, you will not have the negative and positive parts because it goes via a free radical mechanism, but only to understand, only to write the product, you can follow that, isn't it? In fact, this is the one that gives the negative thing has gone to a carbon having more number of hydrogens. Whereas this one is the one that gets a positive charge. It has gone to a carbon that has more less number of hydrogens. So this is how. But only to actually understand that, let me give you the mechanism, a free radical one. But of course goes via anti-Markovnikov addition because we are going with peroxides, sunlight, and all. Okay. Uh, See the mechanism. Now, when ICF3 is considered, this ICF3 in the presence of sunlight undergoes homolytic fission to form iodine free radical and then CF3 free radical. Okay. Now let us consider our propene. So this propene, add CF3 free radical. Okay. It actually goes this way. Again, go for homolytic fission. You get this and this. Now you can just add these two, right? That is how you get a 2-degree free radical. Then CH2, you got CF3, CH2, CF3. To this, again, when just like the addition of HBr, we'll be adding CF3I again. Okay. So this will be, yes, add this here. So minus a CF3 free radical. And that will give you the final product. CH3, CHI, then CH2, CF3. You can see the addition of HBr in the presence of peroxide mechanism. The same thing. There we studied in 3 steps. So this is in fact a 2-degree free radical, right? It is a more stable one. Okay. Next. See, when propene is treated with carbon tetrachloride in the presence of peroxide, you can actually cut it as a Cl and CCl3. Come on. CH3, CH, Cl, then CH2, to which add CCl3. So these are the things that got connected according to anti-Markovnikov. Next, let us take chloroform. The same chloroform with a peroxide. See, this of course is CH3. Let me add hydrogen here, then CCl3 here. This is how things get added. But when the same thing is carried out with CHBr3, I mean bromoform, reaction will be little different. CHBr3 in the presence of peroxide. Here, a bromine gets connected. And to this carbon, CHBr2 gets connected. See, this is interesting. So here you get a hydrogen free radical readily, but here you get a bromine free radical readily as compared to hydrogen free radical. That is the difference. So let me put a star over here. Then, see, when a thiol is added, alkane thiol in the presence of peroxide. Here again, of course, it is the regular one. Hydrogen, then SR. Okay. So these are the things which get added according to anti-Markovnikov addition. All these are, of course, according to anti-Markovnikov. Okay. So these are some of the free radical reactions. Okay.